Hello, everybody. So we are on to our third unit, and it is on exponential functions and logarithmic functions with a splash of something called logistic. So the first learning target is about exponential and logistic. Logistic is something you've probably never seen before, but exponentially you've heard of a lot. You know, population grows exponentially, of course. Like, let's think about Grant Park in Chicago, had a rabbit problem decades ago. Too many rabbits were multiplying, so rabbits grow exponentially. But eventually, but not indefinitely, right? I mean, if that were true, then the world would be covered in rabbits, but that's not the case. So what happens? You know, all these rabbits have baby rabbits, et cetera, and eventually they run out of resources in their area. So Grant Park in Chicago is only so big. So once the rabbits leave the park, they have to face this, Michigan Avenue and the rest of the loop. So they can't really survive that well out there. So that behaves in this logistic way. So a logistic function will behave exponentially up to a point, and then at a certain point, it'll like taper off. So it's pretty good. It's a good function, and it should be new to you. I don't think you've seen it in another class, but we're not going to cover it today, nor are we going to cover it tomorrow, but it is coming up. First of all, exponential. This is the main function of an exponential function. It has a base, which we would call b. The key thing here is that the base will always be positive, 100%. If it's not positive, then it's not an exponential function. And it will never, ever be 1. Why? Well, because if b was 1, then 1 raised to anything is still 1, and nothing is happening. This would just be a flat line if b were 1. If b is bigger than 1, then it's called an exponential growth. And if it's between 0 and 1, then it's called an exponential decay. All right. And then you've got the domain and the range, as usual. The domain is the exponent, and the exponent can be anything. You can have an exponent that's negative, an exponent that's positive, a fraction. It could be 0. It could be the square root of 2. It could be anything. So the domain is all real numbers. The range, however, since we are starting with a positive, no matter what you raise it to, you will always result in a positive. Always, always, always. 3 to the 0. Do you remember what 3 to the 0 is? 3 to the 0 equals 1. What about 3 to the 4th? Whoops. That was Walter Payton right there. 3 to the 4th is 3 times 3 times 3 times 3, which is 81. Obviously a big positive. What about 3 to the negative 4th? What does that do? 3 to the negative 4th, I hope you remember, is the same thing as 1 divided by 3 to the 4th. So the answer is 1 over 81. 3 to the negative 4th is positive 1 over 81. So there's no escape. The result, the range, will be all these positives. Now that's just for the parent function, but we can change this around. We can subtract 7. That means that now the range is everything from negative 7 to positive infinity. Or we could flip this upside down, and that would change the range too. But the starting point for an exponential function, the range will be all positives. And so here are two main graphs. This maroon one is the decay. So as time moves forward, the y values are getting smaller and smaller and smaller. This happens when the b value is between 0 and 1. The blue one is the exponential. It's the rabbit function, the one that we're most familiar with. When x gets bigger, so does y. It grows exponentially. And there will always be a horizontal asymptote, always, with exponential functions. All right, let's dig right in. No calculator, no calculator. We have this function y equals 3 to the x. So the base is 3. And there is an asymptote. Is always a horizontal asymptote, and for this case, it defaults to y equals 0. So it's always y equals 0 unless you shifted it up or down, unless there's some sort of vertical shift happening, and that's not happening here. There's just a horizontal asymptote at y equals 0. The domain for all exponential functions is always all real. And the range, what are all the possible y's? Well, I'm starting with 3, and I'm just raising it to a number. So the result will always be positive, just 0 to infinity. And this is always increasing. If you read the graph from left to right, you will see that the y values keep on going up, 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 and therefore it's never decreasing. So how do we graph this? Well, we have to be smart because we don't have a calculator. So 0 should be your favorite number. If x is 0, what's the result? What is 3 to the 0? 3 to the 0 is 1. So there is an ordered pair at 0, comma 1. When x is 1, well, what's 3 to the first? 3 to the first is 3. So there's another ordered pair at 1, comma 3. And if x is 2, then that's 3 to the second, which is 9, and I can't graph 2, 9. It's too far up there. But that tells me something, and I know that when I graph this, as x gets bigger, the y values are getting bigger really fast. So this is shooting upwards. What about when x is a half? What is 3 to the 1/2? What is that, everybody? That is the same thing as the square root of 3. That's the same thing as the square root of 3. Remember that from Algebra 2? So when x is a half, the y value is 1.73, so like about there. What about when x is -1? What's 3 to the -1? That's not -3. No. It is 1/3. Come on now. So -1, comma 1/3. So about there. When x is -2, what's the y value? What's 3 to the -2? It is 1/9. 1/3 squared. So when x is -2, it's not even as high as 1/3. It's 1/9. So now I hope you can see I don't have to do more. Like when x is -5, the result is 1/3 to the 5th. So it's very, very close to 0. So, but this is more than enough. We know there's a horizontal asymptote right here. We know that when x gets big, the y's are getting big. So this is enough for me to graph. I just try to very carefully go through, oh boy, something like that. So there's our exponential graph. No calculator needed. Now, 3 transformations just took place from that previous one. 3 transformations. What transformations took place? Well, the base is still 3. There was a vertical stretch. I multiplied it by 2. So all these y values are going to be doubled. That's the vertical stretch. Was there a vertical shift? Yes, down 2. So after all these y values are doubled, then you subtract 2. And then was there a horizontal shift? Yeah, this x minus 1, what does that mean? To the right 1. So imagine this graph, first of all, stretched. So every y value gets doubled. So this y value of 1 becomes 2. This y value of 3 becomes 6, etc. All the y values get doubled. Then all the y values go down 2 units. So everything just gets sunk down 2, including the asymptote. The asymptote, which was y equals 0, will now be y equals -2. And you know how the range was 0 to infinity? Well, now the range is sunk down 2 more units. So now the range is from -2 to infinity. The domain all right, and then the domain is still all real because for exponential functions, the domain is always all real. You can raise the exponent, can be anything. All right, let's get back to this. Let's start graphing this. First of all, from all these transformations, I know the horizontal asymptote is at y equals -2. So let's graph that very quickly. That's going to help me. That's going to help guide me. And then I need to pick ordered pairs. So what would be, knowing that I don't have a calculator, what is the smartest x value to choose here? And I hope you chose 1. Because when x is 1, then the exponent would be 0. And 3 to the 0 is 1. 2 times 1 is 2. And 2 minus 2 is 0. That is one ordered pair. Let's do that again. When x is 1, then the exponent is 0. And 3 to the 0 is 1. 2 times 1 is 2. And 2 minus 2 is 0. What's another smart choice for an x value? Maybe 2. 2 is a decent choice because when x is 2, then the exponent is 1. 2 minus 1. So 3 to the 1 is 3. 2 times 3 is 6. 6 minus 2 is 4. And let's see if we can get away with just plotting 2 points. 1, 0. And 2, 4. 1, 2, 3, 4. Let's see here. Let's do one more. Let's just do 0. When x is 0, then the exponent is -1. So what is 3 to the -1 power? That's 1/3. So 2 times 1/3 is 2/3. And 2/3 minus 2 is -1 and 1/3. So 0, -1 and 1/3. So I hope you can see that it's going to be approaching this horizontal asymptote, still shooting upwards very, very quickly. But how this is different than the previous one, oh brother, hope you can draw better than I can, is that now we have an x-intercept, which was new. Here, in this previous one, we did not have an x-intercept. Y equals 0 was the horizontal asymptote that it was approaching. But if you take this and just sink it down 2 units, then of course it would cross the x-axis. So you actually do have an x-intercept. But the horizontal asymptote is still guiding you. It's always increasing. It's never decreasing. 2 more examples, then we're done. This one, and it's the behavior. When what y value is being approached when x gets really, really small? In other words, when you go to the left, these y values are getting closer and closer to what y value? They're getting closer and closer to the asymptote, -2. When x is getting really big, so in other words, to the right, the y values are also getting big. Here, the base. So please pause the video, try to answer all these by yourself, and then play it again. The base here is 3/5. There was no vertical stretch, but there was a reflection over the x-axis when you multiply by that -1. Vertical shift, yeah, it shifted up 3. Horizontal shift, yes, it went to the left 1. First of all, the easy one, the domain, always all real. But the range, normally the range would be from 0 to infinity because you start off with this 3/5, right? But this negative sign flips it upside down. So hold on a second, so normal with 3/5, with the base being 3/5, that would be a decay. So as x gets bigger, the y values get smaller and smaller and smaller. That's what a decay would look like. When time goes forward, the y values get smaller and smaller. But this negative would flip it upside down. Let's see if I can do this. Come on. So that's what that y value, that negative in front, just flips it upside down. And then the +3 raises it up 3 units. So it's going to look something like this. But the horizontal asymptote will be y equals 3. Remember, it defaults to y equals 0, but since we went up 3, now it's y equals 3. And then the negative in front flips it upside down. So that means asymptote y equals 3. The range is now from -infinity all the way up to 3. Those are all the possible y values. It's always increasing. and it's never decreasing. Now, let's erase this and get some ordered pairs in here. What would be a smart choice for x, knowing that you want to do the least amount of work in total, and it is definitely, without question, -1. You should type in -1 for x, because when x is -1, this exponent goes to 0. And 3/5 to the 0 is 1. And then negative times the 1 is -1, plus 3 is 2. Whew. So we've got a ordered pair at -1, 2. I forgot my asymptote. Y equals 3. Oh. Come on. Oh. Hallelujah. All right. Another one. Let's say when x is, what's another good choice for x? 0, I guess. When x is 0. Well, when x is 0, the exponent is 1. So 3/5 to the first power is just 3/5. And then you make that negative. So this is really -3/5 plus 3 is 2 and 2/5. So 0, 2 and 2/5. 0, 2 and 2/5. And that would be sufficient for us to draw, knowing that it has this horizontal asymptote. It does not have a vertical asymptote. It does not. None of these will. When x gets really, really small, when x gets -infinity, the y values also go to -infinity. And when x gets really, really large, the y values get closer and closer to 3. Last one. E, one of the most important numbers in the world. E, especially next year in calculus. Your calc teachers want you to know E. E is a number between 2 and 3. At one point, you were E years old. You have more than E fingers on your right hand. E is 2.718. It's an irrational number. It goes on forever, but it is a naturally occurring number. It kind of what I mean is that when people study phenomena in our world, this number E just does appear. Pi is a popular number, and E, they're both kind of in the same category. They're both real. They are real, but they are irrational. Now, for this one, this is just the parent function of e to the x, so there is no vertical stretch. There's no horizontal stretch. There's no shifting going on. When x gets really big, so 2.7 to like the 100th power is going to be a huge, huge, huge number. Fewer grains of sand on our whole planet than e to the 100. And what about when x gets really small, like -100? Well, e to the -100 is 1 over e to the 100, which is basically close to 0, really, really close to 0. There were no vertical shifts up or down, so the asymptote is just defaulted to y equals 0. So let me graph that before I forget. And then make that a little thicker. And what else? The domain, again, all real. Range defaults all positives, 0 to infinity. The reason why I keep on harping on the domain is because very soon we're going to be talking about logarithms, and logarithms are the inverse of these. So these are going to switch. And it always increases, and this one never decreases as well. So let's find some ordered pairs here. The best ordered pair for sure would be to do 0. When x is 0, the result is 1. Another ordered pair is 1. When x is 1, the y value is e. So 0, 1, 1, E. Remember, E is 2.718 about, so 1, 2.7, something like that. We have an idea of what these look like. We're guided by the asymptote. We're guided by these 2 points. So you do your best to draw an exponential function. All right, thanks very much for listening. Hope that was okay.